going out to a whole bunch. There you go, YouTube, Rumble, Instagram. I'm not sure about Instagram, but anyway. There we are. Okay, are you good to go, Fred? We'll get this TikTok done.
Let's do that. I've just tried to remind myself what we're talking about today.
Rogue planets, dark matter, and
yeah.
Fermi paradox.
The Fermi paradox, yes. All good stuff. Typical Space Nuts fare, if I can.
Yes, it is. Yes, we don't get questions about any of that stuff. Okay. Here we go in 3, 2, 1. Hi there, Andrew Dunkley here from Space Nuts. Hoping you can join us on our next episode or two coming very, very soon. And to explain what we'll be talking about is Professor Fred Watson. Hello, Fred.
Hello, Andrew. Good to see you and good to have a great Space Nuts episode in store with some good stuff like new observations of rogue planets or orphan planets, as they're sometimes called.
Yeah.
Where have they come from? And then we'll talk about dark matter. If you've ever heard of that, I don't think we've really mentioned that before much.
No, not recently. No.
We still don't know what it is. And why we still haven't found any evidence of extraterrestrial life in the universe, and a new look at the Fermi paradox, which asks that question: why isn't the universe teeming with life? So it has been re-examined, and some interesting thoughts in it.
Okay, and in our Q&A episode to follow a few days later, we're going to look at life and death in the universe. It's an interesting sort of concept. It's not really looking at life as in human or extraterrestrial. It's looking more about the life of things in the universe and the universe itself.
Life cycles.
Yes, that's right. And why do black holes grow? Somebody wants to know. A question about space junk and being able to see the Milky Way in the UK. Apparently that's a problem. I've got a feeling it's light pollution that's causing it, or it could be just the fact that the UK is never in sunshine, ever, ever, ever. I'm being a bit naughty there. Fred, I'll go first with the that's all coming up on our next set of podcasts very soon, Space Nuts. I've got a pretty poor dad joke for you. You ready for this?
Okay, go for it.
Did you hear about the insecure physicist?
No.
She was fishing for compliments. That's bad.
Yes, it's terrible. Yeah.
Not even punny.
Funnier than mine is. Or maybe it's not. I would like to ask, why was the star so similar to his dad?
No.
You'll kick yourself with it. Like father, like son.
Oh, that's so bad. It's good. Yeah. Yes. All right. I will pay that. That's not bad. Okay. Thanks, Fred. I hope you can join us very soon. New episodes of Space Nuts coming to a podcast platform near you. Right. That wasn't bad. Like father, like son.
Yes.
Yeah. It's obvious when you say the answer.
It is, yes.
Hello to those watching us live. If you've just joined us, you've missed the best bit, but oh well.
Yeah, absolutely.
Luckily dodged. All right, we might as well get started then.
There's nothing else to do, so that's probably the best thing.
We're live on YouTube and our website, apparently. Oh, just click the videos tab at the top of the page. There you are, spacenuts.com, and click the video tab at the top of the page. I'm going to have a look.
Oh, do you really want to do that? You might.
There's videos. I'll probably get feedback now.
Yeah, yes, you will.
Space Nuts Live with Professor Fred and Andrew Dunkley.
There you go.
I won't press the button, but yeah, there it is.
Don't press any buttons. You never know what might happen.
No. All right, it could throw us into a loop. Boom, boom. All right, here we go in 3, 2, 1. Hello, thanks for joining us. This is Space Nuts, where we talk astronomy, space science, and all the problems of the world that we cannot solve, and a few other things as well. But coming up on this episode, in fact, we are going to look at some new information that's come from, yes, you're right, the James Webb Space Telescope. It has found 6 new rogue planets, rogue or orphan planets. They're out there floating around. They don't have a star. They've got no mum, no dad. They're just hanging around on street corners, smoking joints. But we're going to find out more about these ones. We're also looking at doubts that have been raised about the existence of dark matter itself. Well, if it's not dark matter, what is it? And if it's dark matter, I don't know. There's been a study done and they've gone, nothing to see here. And we're going to look at some new ideas around the Fermi paradox and life in the universe. It's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And unravelling the ravelment that is astronomy and space science is Professor Fred Watson. Hello, Fred.
Hello, Andrew. Good to see you. You're
Good to see you too.
Today.
You're looking rather dapper.
Dapper. Oh,
yes, pinstripes suit you.
Yeah, well, yes, it's the shirt. You see, that's because I spent the morning in far more official meetings than we're in now.
I spent the morning on the golf course.
Well, there you go. Yes, that shows. It does show.
Yeah, well, you can see I'm a bit red in the face. Got some sun. Yes, we had a beautiful day today. Spring has just gone. It's like dropped on us like a giant ball, and it just all the cold weather just suddenly vanished. Yes, very very enjoyable. I probably spoken too soon. Next week we'll have snow.
Except it is coming back. The cold weather's coming back.
Of course it is.
We've had it. We've got 29 degrees here today.
Yeah, we've been up in the
ridiculous for winter.
Yeah, we're expecting. I think we were supposed to get 25 today and 28 on Friday. Yes, it's insane, and yeah, we're still technically in winter. Yeah, I wonder what's caused all that. Let's not go there. But we have got a lot to talk about, Fred. And the first thing is a story that's gained a bit of traction in several websites, and that is a new thing from the James Webb Space Telescope. 6 wandering rogue planets is one headline. Another one says James Webb spots new rogue worlds, orphan planets. I guess we could start off by explaining exactly what a rogue planet is. I think most people have got it in their minds well and truly, but a few might be going, what on earth is that? It's it's some there's all sorts of reasons for them, but they are out there.
That's correct. And I mean, I always think rogue planets it's not a good name for these things.
Makes them sound naughty.
Yes, that's right. It gives them a bad look. Whereas, if you call them orphan planets, then your sympathies are much more with them.
Well, it just sounds sad.
Sad planets, yeah. There's an acronym that I remember writing about a long time ago. They were called FFLOPs. FFLOPs was free floating low something. I can't remember. I can't remember what it was. I'd have to look it up, and I haven't got time to do that now. But I thought, yes, FFLOPs kind of. I think it gave them a sort of tick of failure, or cross of failure, really, didn't it? That they just haven't made it. They're flops, really. They haven't made it. And in a way, that is what this story is about, because whilst we've known about rogue planets or dwarf or orphan planets for several decades now, some of the first were discovered actually using the Anglo-Australian telescope, if I remember rightly, here in Australia, in the Orion Nebula. So the Orion Nebula is a place, it's a region of star formation. It's a place which became sort of reasonably well known for its orphan planets. But the question about them is where they came from. And there are basically two possibilities. One is that they formed in the normal way that planets form, from the protoplanetary disk around a young star. And so, rogue planets, orphan planets would have formed along with their siblings in that protoplanetary disk. And then something happened that basically kicked them out, sent them wandering off into interstellar space with no sun to orbit around. Maybe we should call them banished planets, because that's
Vanished planets. They were caught smoking in the school toilets. That's what it was.
Well, I suppose that's the equivalent of a gravitational interaction with another planetary body, which amounts to the same thing, really. You still get kicked out. So, did they form in the way that all planets form, the normal planetary formation, and then get kicked out by some gravitational interaction? Or did they form as the bottom rung, if I can put it that way, of the star formation process? So when stars form in clouds of gas and dust, which is where we know they are formed, and they're formed by these blobs of this gas and dust collapsing under its own gravity, and eventually that collapse produces a high enough temperature because of compression that you will get nuclear reactions taking place. Now, the clouds of gas and dust where we know stars form are multifaceted, and there is a suspicion that perhaps some of them you get little blobs of gas and dust which collapses as though it was going to form a star or a sun, but it doesn't have enough mass in there, so the compression never reaches the temperatures that you need to click nuclear reactions into being. And so that's what you might call the top-down model, where you've got you start off forming a star, but there's not enough material to form that star, and what you get is something with the mass of a planet, and that is a perfectly reasonable explanation for why these orphan planets or rogue planets exist, and in a way that gets rid of the orphan bit, because they've never had a parent star. They've always been objects that have formed directly from the raw material of stars, that's gas and dust. So this new observation has shed some light on that. And it comes, as you said, from the James Webb Space Telescope. About half a dozen of these orphan planets, rogue planets, flops, whatever you want to call them, have been found without a star to orbit, and they are in the Perseus molecular cloud. It's a region of molecules, as the name implies, which is basically gas, cold gas and dust, and it's in the constellation of Perseus, the Northern Hemisphere constellation. So the planets which have been found have ranged between 5 and 10 times the mass of Jupiter, and this is a sort of critical measurement because there is thinking that suggests anything less than that, than 5 times the mass of Jupiter, would have to have been formed in a bigger planetary system and then kicked out. So there's a sort of lower limit there on the formation of these. And so what you're saying is that, if you were seeing them less than 5 times the mass of Jupiter, then you could point to them having been formed elsewhere in a solar system and then kicked out. But the fact
they were the runts of the litter.
Yeah, in that sense, that's right. Although 5 times the mass of Jupiter is pretty big.
It is. I wouldn't call it that to its face.
No, you certainly wouldn't want to do that. You could get into all kinds of trouble. But so this observation tends to favour the idea that these things have formed as though they were going to be stars, but haven't got that far.
Yeah.
There is another limit that applies to these objects, because anything that's more than 13 times the mass of Jupiter becomes something else. That is what we call a brown dwarf star, because that is the mass in which what you might call low-level nuclear processes kick in. it's basically deuterium burning. They call it fusion of deuterium. So anything above 13 times the mass of Jupiter will be a brown dwarf star.
Speaking of which, Fred, for those who are watching us, I've got a brown dwarf.
Oh, hang on. I'll turn my. Oh, so you do? Yes.
Yeah. It's a terracotta warrior from China.
Yes, that's right. There you go.
But it fits in the palm of my hand. Brown dwarf.
Is it less than? It must be more than 13 times the mass of Jupiter then, if it's because that's the
I don't think so.
But just watch out for that deuterium fusion in its interior.
I hope there's none in there.
At the risk of wondering if you and I are talking at cross purposes here, I'll carry on.
Yes.
So more than 13 times the mass of Jupiter, you've got a brown dwarf. More than 93 times the mass of Jupiter, you've got a star. Because then you've got enough mass to create hydrogen fusion of hydrogen into helium, the normal nuclear process. So it's an interesting set of observations that we've got that might draw a line under the question as to whether rogue planets, orphan planets, whether they form alone in a top-down process, in other words, collapsing star clouds of raw material of stars, or whether they're kicked out of their solar systems. And it looks as though it is the former rather than the latter.
Yeah, so they're independently created, and then they just float off into the ether. And I guess what will likely happen to them is they'll just keep floating around out there, doing not much.
Yes, that's right. Indeed, they will. They will evolve in a slow sort of way. They're almost certainly gas giants. There is just one other sneaky input into this debate that came from these new observations, and that is that one of these rogue planets looks as though it has its own protoplanetary disk. In other words, a miniature version of what the solar system would have looked like in its early history, where the planets were formed, or what a solar system looks like. It looks as though there's a sort of tiny replica of a solar system being formed around one of these rogue planets, which again points to the top-down formation mechanism. In other words, they're formed by the collapse of small clouds of gas in a molecular cloud.
That's fascinating. I also think during this study they found a brown dwarf that had its own planet. So
yes,
what would you call that? That's not they're not rogue planets. It's a you might almost call it a binary system, because the brown dwarf is low mass, the planet's probably quite high mass. The difference between one and the other is one's burning deuterium and the other isn't. Yeah, wow. There's so much, this James Webb Space Telescope is starting to reveal to us, and even though it's, which I've mentioned before, opening up so many more questions, it's also managing to answer some questions, and we're only in the early phases of its role, its mission. Who knows what else we'll discover? But if you're interested in reading that story about rogue planets, just do a search for it. There are so many platforms. Space.com's done something on it, Cosmos Magazine. Or if you want to put yourself to sleep and read the whole thing, it's in the Astronomical Journal. That's where they publish the official paper. Yes. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Now, Fred, doubts have been raised about the existence of dark matter. We get a lot of questions, surprisingly, about dark matter. People wanting to know what it is, how we've managed to find it. We haven't actually identified it. We just sort of know it's there because it has to be, otherwise things wouldn't add up. But now a new study has been published that's basically said, hey, we've looked for this stuff and can't find it, can't exist.
Yeah, nobody's saying it can't exist.
No, I know. I just threw that in there for topical humour.
Well, yes, yes. Don't misquote anybody, though. That would be
No.
So, yes, so it's some results from a dark matter particle detector, which is looking specifically for one candidate particle for the dark matter problem. So, quick recap, without there being something called dark matter, galaxies wouldn't hold together. They'd rotate too fast to hold themselves together, and that's one of the main reasons why we think dark matter is present, plus the fact that we see evidence for it with gravitational lensing and things of that sort. But it's not detectable by normal means because it doesn't seem to interact with normal particles in any way other than by gravity. It doesn't interact from a nuclear standpoint. It doesn't interact from any kind of electromagnetic interaction, in other words, interaction with photons. None of that, doesn't want to know. But it seems to exist. Now, multiple candidates have been proposed for what that particle might be. And indeed, some people think there might be a whole zoo of different dark matter particles, like there are with normal matter particles. When you think of the 16 fundamental particles, 17, I think, if you throw in the Higgs boson, in what we call the standard model of particle physics. So one of the proposals has been something called a WIMP. The WIMP is the weakly interacting massive particle. And a WIMP has particular characteristics, sort of particular expected mass in order to provide the kind of gravitational pull that we think dark matter has. And so this particular experiment was tuned to look for WIMPs, specifically to look for WIMPs. And it's a detector that is called Lux Zeppelin. And I think that's an acronym, but it's usually just contracted to LZ, Lux Zeppelin, or LZ, if you're on this side of the Pacific. A number of scientists have been involved with this, US scientists. It is basically a US facility. It's located I was going to say a mile and a half, but it's actually more like a mile, 1.5 kilometers underground. At something called the Sanford Underground Research Facility. And it basically consists of an enormous tank of xenon and a lot of very sensitive light detectors, photomultiplier tubes, as they're called, to detect any collision that might be produced between a WIMP and a normal particle that would produce electromagnetic energy, in other words, light. And so people might be thinking, wait a minute, Fred just said that it doesn't interact with normal particles. Now he's saying that it does. And the bottom line there is that we think it might do, but very, very rarely. In other words, there might be very sparse numbers of interactions between normal particles and the fabled dark matter particles. And what that then leads you to be able to predict, okay, if you've got an interaction between, say, a proton and a WIMP, what will you get? And the theoretical nuclear physicists who think about this stuff can predict what kind of gamma ray spectrum or light spectrum you might get from such an interaction. And that's what these detectors are looking for. Those characteristic signatures that you might get from a hypothesized WIMP hitting a real particle, something that we know is not just hypothetical.
Yeah.
Well, they have run this experiment now for, I think, 280 days altogether, and not found anything. And so that means that they can say that these WIMPs don't have a mass bigger than 9 giga electron volts. So a mass, when you're talking about subatomic particles, is measured in electron volts. 9 giga electron volts is actually quite high. For example, the particles that you might detect from the Large Hadron Collider are in the basically they're in the tera electron volt level, so they would detect more than this. But this particular experiment is saying nothing bigger than 9 giga electron volts is a WIMP. They don't exist if their mass is bigger than that. However, that's just
I knew there'd be a but.
Yeah, because a different detector might be able to detect more massive particles, but we haven't got that yet. However, again, one is coming because the university, actually, I think it's a consortium of universities in Australia, are putting together a detector known as SABRE, a nice name, SABRE, and it's down inside another mine, this time in Stoyle in Victoria, well-known town in Victoria, in the southern part of Australia, and that will come on stream next year. The SABRE detector will come on next year. It'll come on stream next year, and it has a different category of detection for dark matter. It's looking for something different rather than just collisions. It's still got a target, not liquid xenon like the LOX Zeppelin has. It's a target that is a mixture of sodium and iodine, so different chemicals that might react to some sort of particle interaction that they think they may be able to detect. I think the Stoyle SABRE detector scientists are a bit more optimistic that they might find something with their new detector when it comes on stream next year.
So the bottom line is they've run this 280-day study and basically said, look, we can't find anything that you could identify as a dark matter particle, and it falls within the search area of these parameters, but we can't look any bigger than that, so we can't find them. They don't exist in these in this spectrum, but there could be particles that are larger than that we can't find, and we haven't got a machine that can do it yet, but there's one coming.
That's the bottom line. Very beautifully put, Andrew. You ought to be a journalist. I'm
too honest for that.
Yeah, you probably are. The bottom line is the fact is that we know there is something there because astronomy tells us that we're missing something completely. And the best candidate from all the research that's been done is some kind of subatomic particle. And that's why you've just got to do these experiments and hammer down or maybe open up the space within which you're looking. And as you say, it's these various parameters that are being defined by these different instruments. So I hope we'll talk about Stoyle next year when it's switched on. Maybe the first thing it'll discover is a dark matter particle.
Well, we hope so, yes. It would be good to find one, and then we'll ask it a lot of questions because it needs to come up with answers.
Yes.
We've been sitting here wondering for so long now. If you'd like to chase up that story, you can look it up on the ABC News website. That's ABC Australia. But you can also go to the LZ Dark Matter Experiment website, which I found while you were talking, Fred, lz.lbl.gov.
Oh, good.
So that's got everything you need to know about the study and how it worked and what they did and all these big numbers that are too hard for my brain. But check it out. This is sorry.
Excellent.
Yes, it is. It is. This is Space Nuts with Andrew Dunkley and Fred Watson.
Listen, Tranquility Base here. The Eagle has landed.
You're listening to Space Nuts, the podcast about astronomy and space science with Andrew Dunkley and Professor Fred Watson.
Okay, Fred, just as elusive as dark matter, although the difference being we probably know that dark matter exists, we don't know if extraterrestrial life does. And once again, the Fermi paradox has been put under the microscope or the telescope or whatever scope you want to use. And questions are being asked, some new ideas about life in the universe or not. What's going on?
Yes, a paper by a person by the name of, I guess it's Vorhin Rakic.
Sounds about right.
Probably really mangling that, really. Who is a scientist. Vorhin is a Serbian philosopher. He's somebody who thinks about these things and has published a paper in the Journal of Astrobiology, which I have in front of me at the moment. The International Journal of Astrobiology. The paper is called "A Non-Anthropocentric Solution to the Fermi Paradox."
Oh, I like the name of that.
Yeah, and that's right. So it means we're thinking in a too limited a fashion. That's the bottom line. That that extraterrestrial life may have so different a set of characteristics to human or to terrestrial life that we're just missing it completely. And that's what he means by non-anthropocentric solution.
I haven't heard the whole story yet, but I reckon he's spot on.
Yeah,
I think that could well be the answer.
It's sort of what what people urge us to do. We get questions from people saying, but have you thought of life that was based on silicon rather than carbon and things like that? And yes, we've
methane.
And methane.
Yeah, we have talked about it.
All of those, we've thought about that. But Professor Rakic is urging us to be even more broad in our thinking. So what he suggests is that the normal explanations, and there's several people have proposed explanations, that they're all too anthropocentric. They're putting humans in the center of the picture, as phys.org has put in their article about this.
Yeah.
And suggests that alien life might be unobservable to the senses that we as humans have developed. This philosopher is clearly a very profoundly thinking person in the field of this kind of approach. He's basically works at the Center for the Study of Bioethics, University of Belgrade, and clearly spent a lot of time thinking about this. I'm trying to think of how we can summarize it. Let me just go back to the abstract for his paper, because he's classifying the solutions to the Fermi paradox in 4 different categories. And this is what his paper discusses. So the categories are, first of all, exceptionality solutions. That means we are exceptional, that there isn't any other life in the universe. Number 2 is annihilation solutions. That is that extraterrestrial intelligence doesn't last very long. It gets annihilated one way or another, either by natural causes, a supernova wiping out life, or
self-infliction.
Self-inflicted ones, exactly, the ones that we naturally think about, wars or even viruses, runaway viruses, things of that sort. And then communication barrier solutions. Sorry, I said there were 4. That's only 3. That means that there's no ability to communicate. And I can imagine one scenario with that might be, for example, if there is extraterrestrial intelligence in the oceans of Enceladus or of Europa, where there's no way of penetrating that ice covering, the glass ceiling, if I can put it that way. You can't get through that. So we would never know about that. So it's a communication barrier. But then he says, really, what we've got to do is take humans out of the equation altogether, forget about human life, and look at the broader context, what sort of life there might be, whether it's life that exists as inorganic matter or, some sort of entity that we are not capable of perceiving. And it's. I think what he's doing is setting the groundwork for possible future thinking about this. And in fact, the last line of the abstract of his paper is, in the light of the revolutionary developments in theoretical physics, it is likely that in the future, these developments will be reflected in increasingly non-anthropocentric solutions to the Fermi paradox. In other words, people thinking more outside the box.
You know what? I think that's a great way to. It's a great idea to consider that, because I think he went on to say that some of these entities could exist as made up of dark matter or dark energy, or the things we've been talking about that we can't detect.
Yes,
but
that's right.
That's a possibility. And I love the way he talks about how we perceive the intelligence of other creatures on Earth, like whales and dolphins. But what do they think of us? Do they look at us as intelligent?
Yes.
Maybe they don't. Maybe they just go, look at these dimwits, they can't even swim.
That's right.
And how insect life perceives humans. Do they look at us as intelligent creatures? I think not. They probably they may not even recognize us as alive. And that's where he's coming from.
Yeah, that's right. That's where he's coming from. It is. I think you're clearly enamored by the ideas that he's putting forward, as am I have to say. And,
it's an interesting way of looking at it, and it sort of opens the whole world of science and technology and astronomy to being more philosophical, being using philosophy as a way of analysing possibilities, probabilities, and even things that are so far out of the norm that we haven't even looked there, but maybe we should.
That's right. I feel I've not done this professor a service in terms of my explanation of his theory, but the paper actually, if our listeners can check it up on it's one you can look at online. See, in the International Journal of Astrobiology, it's called A Non-Anthropocentric Solution to the Fermi Paradox. It's very beautifully laid out. I'm not used to reading papers by philosophers, but this is really neat. And the three types of solutions that I mentioned, he lists them here. The exceptionality solutions include the Earth is an exception, or intelligent life is an exception. And that's the one that I've tended to trot out a lot in recent times. The annihilation solutions include periodic annihilations of intelligent life caused by natural events. Advanced forms of intelligence have the tendency to destroy themselves or to destroy others. And then the communication barrier solutions, of which there are many, they broadcast signals that are only detectable for a short space of time. Extraterrestrial intelligent life may be incomprehensible to humans. That's what the one you were talking about with regard to insects and things. They may reside too far away from humans. It's a really interesting list of reasons why the Fermi paradox might still be a paradox. And then the alternative solution that he presents is itself a really interesting set of reading. I'd urge anybody who's interested in this problem to have a look at the paper. Yes,
indeed. Yeah, you can read the story on phys.org, phys.org as well. So, or the International Journal of Astrobiology. Yeah, it's a good one. It's a really fascinating story. Gets you thinking outside the box. Love those sorts of theories. That wraps it up, Fred. Thank you so much.
It's a great pleasure, Andrew. It's always good to talk about these things, especially when we get ideas as stimulating as that.
Yes, I'm sure questions will come. Yes. And don't forget, if you want to follow us on social media, we've got the Space Nuts podcast group Facebook page, our own specific Facebook page. We're on Instagram and YouTube. And don't forget to hit subscribe if you're a YouTube follower. And thanks, Fred. We'll catch you real soon on the next episode, answering some questions. We'll see you then.
Sounds great, Andrew. I look forward to that.
And thanks to Hugh in the studio, who had all the answers to all the questions we asked today, but we don't let him on the show because we just think he's too clever. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.
Keep saying that word, quality. Okay.
It's embarrassing, isn't it?
All right. Now, let me just get my ducks lined up here. I've got 2 text questions and 2 audio questions today.
You do.
If we can manage that.
Yes. Had a look at them.
Yeah.
Good stuff. Where are they? I've lost them now.
I've got them.
Yes, I got them too.
All right. Let us begin in 3, 2, 1. Hello again. Thanks for joining us on Space Nuts. Andrew Dunkley here, and it's a Q&A edition. That means that we're going to answer questions, or we're going to pretend to, or we're going to refer them to a future episode for possible answering or not. Or maybe we'll just put them in a bin. I don't know. What do we got today? We're looking at life and death within the universe, not the life or death of people, or other entities for that matter, but maybe the life and death of planets and galaxies and maybe the universe itself. What's that all about? We'll tell you. We're also going to look at how black holes grow. That question's been asked. Another question about space junk and seeing the Milky Way in the UK. How do you do it? You get a very tall ladder to get above all the smog and the clouds. That's what I reckon. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And it's good to have Professor Fred Watson here to answer all of those because I haven't got a clue. Hello, Fred.
Hi, Andrew. Neither have I, really.
Well, we'll do our best.
Don't worry.
Yes. We have a homework segment that we occasionally do when a question gets too hard.
That's right.
Might take us 3 or 4 months to get back to you, but we do it. We do it. What's the rush? Shall we begin?
Well, why not?
Okay. This first question comes from Trevor. Trevor's in Port Macquarie, which is up on the mid-north coast of New South Wales, Australia. A horrible part of the world. Nobody wants to live there. I mean, they've got beautiful green trees and subtropical forests and white beaches and fishing. And why would you want to live there? Okay, Trevor, nice to get your question. Hi, Andrew and Fred. Everything in the universe is born at some point and has a lifespan. On Earth, at the end of their life, plants and animals return to the soil from where they came. In space, suns and planets live and die and eventually become part of the space around them once more. So could this be true for the entire universe? We think we know that the universe was born in the Big Bang and that it will probably die at some point in the future. So I'm wondering if, over the eons of time, could the black holes that seem to be at the middle of every galaxy eventually pull everything currently in the universe back into one singularity, at which point we would have another Big Bang and a new universe would be born? Many thanks for your program. I listen in bed every night and it helps me go off to sleep at least twice a week. I'm glad we can do that for you, Trevor. We put him to sleep, Fred.
That's right. And that's something I'm really good at.
Oh, boy. I'm sure he didn't mean it that way.
I'm sure he didn't know. Look, Trevor, great to talk to you. You have, as you might know, in Port Macquarie, a brand new, marvellous science centre in the middle of town which is being opened a little bit later in the year. It's on the site of the old observatory there, which I was always very fond of, and indeed was its patron. And I think I might be the patron of the new Science Centre as well,
Oh,
which is
wonderful.
brilliant. And so that opens in a couple of months. So make sure you go along and check it out, Trevor, because you're in pole position to do that up there in Port Macquarie. And the answer is, well, yes, it's true. Everything seems to have a life cycle. And the theory that you've mentioned, that the gravitational pull of everything in the galaxy, in the universe, might eventually cause the universe to collapse back on itself into another singularity.
The Gnab-Gib.
The Gnab-Gib, that's right. The opposite of the Big Bang. That's the name coined by Brian Schmidt before he did his Nobel Prize-winning work. We usually called it the Big Crunch. The idea was that everything would eventually collapse back on itself, and would be a big crunch, which may have spawned another Big Bang, and that would be a new universe being reborn, exactly as you've said, Trevor. What basically threw cold water onto that argument was Brian himself and other colleagues in the United States, who together in 1998 discovered that actually the universe, its expansion is not slowing down, as you would have had to have if you're going to get a Gnab-Gib or a big crunch. It's accelerating. So the accelerated expansion of the universe really knocks that on the head. And it also tells us that there is something in the universe that is causing space to accelerate, not just expand, but to expand ever more rapidly. And we call that dark energy. And if you thought dark matter was a mystery, wait till you get to dark energy. We really have very little idea of what it is. It's some sort of vacuum energy. It's some kind of energy of space itself. The more space you get, the more energy you get, and it's causing the universe to expand ever more rapidly. So it looks as though the universe may never have an ending if it just keeps on going and expanding, unless the thing that some other people have hypothesized, that one day space itself might just get so stretched by the accelerating expansion that it fractures, and you get something called the Big Rip. And the Big Rip is another possible end to the universe, when space itself just gets ripped apart.
Well, yeah, that seems to be the popular opinion at the moment, doesn't it?
It is, yeah. The Big Rip is a little bit hypothesized, but certainly the accelerated expansion is taken as fact now, since that discovery was made. It's not just the observations of supernovae, exploding stars, that were what allowed that discovery to be made, but many other observations of the state of the universe, if I can put it that way, imply that the dark energy is there.
Okay, there you are. So in regard to his question about life cycles in the universe, we are seeing that, and eventually everything's going to finish in terms of the physical forms, the stars, the galaxies, the black holes themselves may well, in billions upon billions of years, evaporate, because they are burning their energy. They're getting weaker over time. It's just a very slow process. But the universe as a whole, that's a different question, I suppose.
Yes, that's right. So you're right in that the kind of life and death processes that involve stars, and stars are the main kind of matter in the universe, apart from dark matter. They're the way we detect matter in the universe anyway. That life and death cycle is well known, and when you look forward perhaps 100 billion years or so, all you've got is dark remnants, black dwarfs we call them, remnants of stars, and probably a lot of black holes as well. So everything's kind of dead and dormant. There's no black holes are not feeding because there's nothing for them to feed on. So it becomes a very boring universe indeed. And maybe a Big Rip would be the fitting end for a universe like that.
And once everything's expanded beyond our capacity to see them, no astronomers, Fred.
Damn.
Yeah. You'll have to retire then.
Yeah, I'm just a dying breed. Oh, that's terrible. Never thought of
Yes. How many gazillion years away is that? Yes.
that.
Anyway,
Yeah, quite a few.
we're in no rush. Thank you, Trevor. Hope you're enjoying Port Macquarie. Lovely, lovely place it is. Let's go to our next question. This one comes from David.
Hey, Fred and Andrew. This is David from Seguin, Texas. Just sitting here in bed thinking about black holes and questioning how is it that black holes grow. Like when a black hole over time becomes a supermassive black hole, how is it that they grow? Because if their gravity can suck in even light and they're supposed to be infinitely dense, why don't they just stay the same size and just continue eating? Why do they grow as they eat? Like, what is it that's growing? Thank you guys. Love the podcast.
Thank you, David. Yeah, it's a tough nut to crack, isn't it? The old black hole. What's it eating? How's it getting bigger? They eat each other, or they merge. And we know that. But yeah, it's a good question. Why don't they just stay the same size? Why do they keep growing? What is causing that? What are they actually eating?
Well, yes, I think the issue is not so much what they're eating, because we do know that they gobble up anything that's
basically anything they can catch.
Yes, that's right. Not that they go chasing around the universe to find them, but
no, they're more like a trapdoor spider, aren't they?
Yes, or indeed a huntsman spider, which also sits and just grabs things. But so that all goes into the black hole. All that debris, stars, gas, dust, other black holes occasionally, all goes into the black hole, apart from what's shot out, by the way, by the magnetic fields that give you the jets from an active black hole. But the question's really about why doesn't it grow? Now, it doesn't grow in physical dimensions because, by definition, a black hole has 0 dimensions. It's a singularity. And so its volume is 0. And we know, I think the way we define a black hole is a point in space of infinite density. So its density is infinite. Now, density is mass over volume. Density is infinite because volume is 0 and you're dividing something by 0, which produces infinity. That's the density. But that says nothing at all about its mass. And the mass is what changes. So it's not the size of the black hole, but it's mass that changes.
Okay.
So they do grow, but they grow in mass. And that's how we get the supermassive black holes, because they've been at it for a long time and accreting this material. So, they do grow. They don't get physically bigger. Their mass gets bigger. And in turn, the event horizon gets bigger. So that's the bit that delineates where you can't penetrate. Nothing can penetrate out of it, not even light, is the event horizon. And so as a black hole gets bigger, its event horizon grows and grows and grows, even though it's still a singularity, but its mass is going up, and that causes the event horizon to swell.
Okay.
Yeah. So
and you can do this experiment at home by eating 100 donuts. It's exactly the same thing. Your mass increases.
It does, but usually your volume does as well if you do that. Yes, I won't do that any further.
Okay, fair enough. So what was the answer to the question? The mass increases, but the black hole doesn't.
The dimensions don't. The dimensions of the event horizon do, because they're linked to the mass. So it's the mass that increases.
Okay. There you go, David. You can go to sleep now. sitting in bed trying to figure out black holes. That's self-inflicted torture, that is. But yes, at least somebody's trying to figure it out. A lot of people are trying to figure it out, David. Thanks for the question. Lovely to hear from you, and I hope all is well in Texas. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, Fred, we've got another audio question, this one a little closer to home, from Mikey.
Hey, Fred. Hey, Andrew. This is Mikey from Illinois again. I was wondering about space junk. There's a lot of it around Earth right now, and there's only going to be more, come the future. And if nothing ever gets done of it, I was wondering if somewhere in maybe the distant future, all of this space junk would kind of coalesce and the Earth would maybe have its own artificial ring system, kind of like Saturn, but just instead of ice, rock, and dust, it's junk. Yeah, just something that kind of crossed my mind. Wonder what you guys think about it. Thanks, guys.
Yeah, that's a really interesting thought. And I mean, it's out there. Some of it re-enters, some of it burns up. Some of it's just floating around out there, and it can be as small as a fleck of paint. But it's moving at a rapid speed, and it has had a few close calls and caused a few problems from time to time. In terms of dealing with it, it's every nation's responsibility to look after their own stuff, isn't it? Or every entity's responsibility.
Yes.
Although that's only a recent law, and we're still, grappling with it. We've been experimenting with ways to collect this stuff, but I think there's just too much stuff.
Well, it's not that there's too much, it's that it's kind of spread all over the place.
Yeah.
And space is big, as Douglas Adams put it. But, I was just thinking about this, Mikey's point, and in a way, the Earth already has a ring of debris because it's the geostationary satellite ring. That's where there are very large numbers of satellites. I don't know the total number that's in geostationary orbit, but it's quite large. And beyond that, there is what they call the graveyard orbit, where geostationary satellites have to be pushed out into a graveyard orbit once their useful life is over. And it's a fairly stable orbit, one that's not, being perturbed so that a satellite will collide with another satellite. So we've already got a ring, the geostationary satellite ring. Most of them are in one piece because we use them every day for communications. But in terms of the low Earth orbit and mid-Earth orbit spacecraft, yes, there is a lot of debris around because these spacecraft collide with one another from time to time. It's, as you said, flecks of paint, everything upwards from flecks of paint. And it just begs the question whether at some time in the future they would actually coalesce into a ring, the orbits of these things would flatten out, so that rather than having orbits at all inclinations, they're going all around the Earth, so the Earth is like inside a shell of space debris, whether it would flatten out into a ring. And I suspect it would in the very long term, that you would end up with a ring of space junk. However, we're a long way from that. I think the thing about the low Earth orbit stuff is that will burn up before we ever get to that stage. So they'll re-enter and burn up and cause pollution in the upper atmosphere, which we now know is happening, detecting aluminium and other stuff like that in the upper atmosphere that comes from re-entering spacecraft. But that's a vapor rather than a solid entity like a ring. So I think the answer to your question, Mikey, is we've got a ring already, and most of it's useful, but some of it's not.
No, and long term, maybe some of the stuff that is orbiting by default and won't return to Earth may well become a ring.
Yes, that's right.
Assuming we don't find a good way to clean it up in the meantime.
Yeah, I mean, we could, there's many projects that have been launched and some have actually been launched into space, but they're ways that you can either throw a grappling iron or a net or something at a piece of space debris and slow it down so it does re-enter the atmosphere. That's becoming, or maybe it's too early to say it's becoming, but it will become a standard procedure, I think, especially for large pieces of debris that if they re-entered in an uncontrolled fashion, they could do damage. I think that's going to be the norm. It's also the norm, as you hinted at, that any nation that launches anything into space, or any organization that launches anything into space, has to demonstrate that they've built in a way of deorbiting it. In other words, they can get rid of it. And that, I think, has been in place for quite a few years now. So in the long term, we're in better shape than we are at the moment. Hopefully, the space junk situation will improve.
Indeed. All right. Great question, Mikey. Thank you very much. One more question, possibly two. I don't know how we'll go for time, but we've got a question without notice from YouTube, I assume, or something to that effect. But this one coming from Ian, who is in Cambridge. Hi, Andrew and Fred. I asked a question last year about not being able to see the Milky Way. I still haven't seen the Milky Way here in the UK. However, there are some photos on social media showing the Milky Way high in the sky above Stonehenge. Are these genuine? I would have thought from the UK perspective, the Milky Way would be low in the southern sky. Thanks for the great podcast, Ian. Well, you're from the UK, Fred, so you know the lie of the land and
the lie of the stars.
The lie of the stars in perspective to the positioning of the northern hemisphere. Can you see the Milky Way from the UK even on a clear night?
You can. And the Milky Way, it goes all the way around the sky. So everywhere on Earth we'll see it at some point. The best time to look there's two kind of good times, I suppose, from the northern hemisphere is the middle of winter, because the Milky Way stretches right up, goes past Orion, goes through Cassiopeia, all those constellations. It goes right, basically from north to south across the sky. It's in the middle of the year as well. You can see it quite well. I think what Ian is really meaning, though, is the center of our Milky Way galaxy, which is the brightest part of the Milky Way, which goes directly overhead here in Australia, but it only skirts the southern horizon in the northern hemisphere, certainly at the latitude of the UK. So you can see it. I've observed Sagittarius, which is where the galactic center is. I've observed it from Scotland, actually, but it's been very, very low down in the sky, and very difficult to see because there's pollution and light pollution and everything there. But the problem, but the Milky Way itself goes all the way around the sky and is visible, as I said, best in midwinter. In fact, in the middle of summer, there's too much daylight. The nights last too long. Or the days last too long. But the main thing is to be away from light pollution. And that's because the Milky Way, as seen from the northern hemisphere, is fainter than it is in the south, because we've got the galactic center where it is richest. Milky Way is at its brightest. So you are right in that the Milky Way is fainter in the northern hemisphere, but it's still visible. And on a dark night away from city lights is pretty impressive. So that picture of the Milky Way over Stonehenge would not necessarily be a fake.
Okay, I've looked at a few here, and one of them's referring to a photograph on a summer night at Stonehenge, and it's showing the Milky Way vertical. Yeah, how does that sound to you?
That would be right. It would be vertical.
Okay.
As it is in winter as well, on a midwinter night.
Okay. There you have it, Ian. So it's probably genuine. There'd be a lot of others out there that have been constructed from superimposed photographs, but yes, it is a possibility. Thanks for the question. One quick one without notice, Fred, comes from, I think TTJ has messaged us before. He's just got home from work. I do have a question. Does the early spring affect viewing of the skies in any way?
Only weather-wise. We've got probably warmer weather that should produce drier atmospheres and give you a better view. I noticed I've got a bit of a weather station on the wall. I noticed the pressure's low actually at the moment. It's much warmer than it should be in winter. The air though is very dry compared with what it normally is like, and that normally gives you better viewing, less twinkling in the sky, because the amount of turbulence in the atmosphere settles down when the air is drier.
How about that? There you go, TTJ. Thanks for the question at the last minute, and he's in Sydney as well, Fred. Probably across the road from you.
Could be indeed.
Yeah. Wrestling goannas. Yeah.
Yes, that's right.
And a reminder to anybody who wants to send in a question to us to go to our website, because that's where you send them, and you can do text questions. Just click on the AMA tab or link at the top. You can also send audio questions that way, or on the right-hand side where there you would usually be send us your voice message, and it's not there today. Don't know what happened to that. Probably my computer doing silly bugger things like it tends to. But yes, we welcome your questions for our Q&A episodes of Space Nuts. Keep them coming. Thanks, Fred, as always. It's a great pleasure.
Great to talk to you, Andrew. We struggled through and we got some good answers there, I think.
Yeah, I think so. And we made them all up as we went along. We didn't even have to sit down before the show and work out fake answers. We made them up as we went along. It was brilliant. We're getting better at this. Thanks, Fred. We'll see you soon. Fred Watson, astronomer at large. Thanks to Hugh in the studio, who sent us one question. Yeah, we can't tell you anything about that at all, Fred. Hugh, we don't know the answer. Talk to your electricity provider. And from me, Andrew Dunkley, thanks for your company. We'll see you again soon on another episode of Space Nuts. Bye-bye.
Space Nuts.
You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at bytes.com.
This has been another quality podcast production from bytes.com.
And thanks everybody who watched us live.